Hello, welcome back to MA211. Today we're going to talk about direction fields and phase lines. The idea behind both of these is to get some idea of how a solution to an ODE behaves without actually having to find an expression for the solution to an ODE. So remember that the solution to an ODE is a function, right? So solution. The solution to an ODE is a function. We can describe functions lots of ways. We can give an explicit formula for a function like f of t equals 3t squared plus 2. That's what we would like best if we could find an explicit formula for evaluating the solution to an ODE. You can also describe functions through graphs, right? You can describe a function by drawing a graph of it. And that's really our goal. Today we're going to try to draw a graph or an approximate graph of the solution to our ODE without ever finding a formula for evaluating the function. Okay, so let's get started. So suppose I start with this ODE, y prime equals y squared minus t, right here. And let's just imagine for a minute that you have a solution going through the point time 2 and then y value 1. So if that would mean that y of 2 equals 1. So let's see, what would that mean? If I move down here, this is my y-axis, this is my t-axis. If I have a solution such that y of 2 equals 1, that means at time 2 it takes on value 1, so it's going through this point right here. Right? This is the point 2, 1. Okay, what would that mean? Well, if we have a solution going through the point 2, 1, then what would that mean? Since y at time 2 equals 1 and y prime at time 2 is equal to, since it's a solution to the ODE, it's going to be equal to y at time 2 squared minus the time 2, which is equal to 1 minus 2, that's negative 1. So what's this mean? That means that if you have any solution passing through the point 2, 1, then it must have slope negative 1 at that point. So we could draw roughly a graph of the solution in that little neighborhood, right? So right around the point 2, 1, our solution must be headed down with a slope negative 1 right there. All right, so we could do this a whole bunch of times, right? We could go ahead and say, well, what happens if our solution goes through lots of other points? What if it goes through the point 1, 1? What if it goes through 1, 2? What if it goes through 1, 3? Or 1, 0? So let's try to see what would happen if our solution goes through all these different points. And then we'll get some information from that. All right, I'm going to go ahead and fill out this table for us. Okay, so we filled out this table, and what this is telling us is if a solution to the ODE passes through the point 0 or 1, 0, then at that point it will have slope negative 1. If it passes through 1, 1, then it'll have slope at that point 0. If it passes through 1, 2, it'll have slope 3. And I've done all of this again just by plugging in t and y of t into this, into the right-hand side of the ODE here. So let's go ahead and turn that into something we can look at. So if I draw again my t-axis and my y-axis, Let me see, I know what happens if it goes through 1, 0, 2, 3. There's a dot here, a dot here, a dot here where I've evaluated y prime at 1. Alright, so these are the places where I've evaluated y prime. We know if a solution goes through 1, 0, the solution will have slope -1. So like that. If a solution passes through the point 1, 1, it'll have slope 0. So any solution passing through this point will be staying flat. If it goes through 1, 2, it'll be headed up with slope 3. And if it passes through 1, 3, it'll be going very steeply up. It'll have slope 8. Now if it goes through 2, 0, you'll have slope -2, so a little more steep. 2, 1, it'll have slope -1, so less steep. 2, 3, it'll have slope 7. Oh, 2, 2, it'll have slope 2. Well, let's just say that's 2 and that this is 7. If it passes through 3, 0, you'll have a pretty steep negative slope. If it passes through 3, 1, you'll have a little less steep negative slope. Through 3, 2, you'll have slope 1. So like that. And through 3, 3, you'll have slope 6. So like that. Now when you draw this information on here like that, this is called a slope field. And from the slope field we can get some information. We can get an idea what solutions look like. Now suppose a solution passes through a point right here. That's not what I wanted. Suppose it passes through a point right here. Does the solution go like this? Well, no. No, we know that any solution that passes through this point has a big positive slope, and this function seems to have a slope 0 at the point 2, 3. Right? In fact, it looks like if our solution starts here, it must behave, so that's not the solution we want. If a solution starts there, it must behave more like this. It must be going that way, right? Actually, up here, we don't really know what the function must be doing up around here because we haven't evaluated any slopes up there. But we know down here that the solution must be increasing. Okay, what if a solution starts right around here? Well, then it must be going, you know, roughly in this direction, and then it must be heading down like that. So that's an idea of what that solution, of what a solution that starts here, that's an idea of what it must do in time. Let me see, a solution that starts here looks like it must start pretty flat, and then it's tough to know whether or not it starts going down or it starts going up. If we evaluated the slopes at more points, we could get a better idea. But I would guess that it starts going like that. Okay, so from a slope field, we can get an idea what solutions to our ODE look like, even without actually finding a formula for the solutions to the ODE. So, as you might expect, Maple is good at evaluating these slope fields. It just has to evaluate the right-hand side of the ODE a whole bunch of times. So let's go ahead and use Maple to do this. Okay, so what you want to do is import DE tools first. So with DE tools, hit enter. You'll see a whole bunch of stuff that you've now imported. You want to do a DE plot. Type in the DE that you'd like to plot. So that's y prime of t equals y of t squared minus t. Okay, you want to type in the unknown, y of t. You need to put in bounds, t equals 0. These are the time bounds that you want plotted, so maybe t goes 0 to 3. And y, this is the other axis, 0 to 3. And see how it goes. And here we have a nice phase port, or a nice slope field. You can see it looks a lot like ours, but a whole lot better. Just a whole lot more points in there. If you want, you can even trace out what solutions to initial value problems look like. So you can say, go ahead and plot what happens if y of 0 equals 1. And you can see it's highlighted what the solutions do. You can put 2 on the same plot by just including more. So what if y of 2 equals 0.5 maybe? And there you go. All right, so that's it. That's all there is to plotting slope fields.